Hi there, in this video we're going to look at the Laplace transform of the cosine and sine functions. Now, from the previous video we've seen that the Laplace transform of e to the j omega t can be written as 1 upon s minus j omega for the real part of s greater than 0, and we've seen that the Laplace transform of e to the minus j omega t is equal to 1 upon s plus j omega for the real part of s greater than 0. Now we can use the trig identity cos omega t equals e to the j omega t plus e to the minus j omega t all upon 2, and that allows us to find the Laplace transform of cos omega t, because we're able to say that this is equivalent to saying just 1 times and 1 times e. Okay, so we're replacing the 1 here with a half, so this is going to give us a half over s minus j omega plus a half over s plus j omega. And when we take the denominator, common denominator, s minus j omega, s plus j omega, then we'll have a half s plus j omega plus a half s minus j omega. And again, the denominator will have s squared, and the j omega, the s j omegas will cancel, and the last two terms here will have omega squared, and we'll have the root of -1 times root of -1, which is -1, and it's a negative of it, so it's positive, so we'll have positive omega squared. And in the top line we'll have a half j omega minus half j omega, which is 0. We'll have half s plus half s, which is s. Okay, so that's for all real s greater than 0, and that's the Laplace transform over cos omega t. Okay, so that's the first one that we're looking for. So we'll go and we'll have a wee look at this in MATLAB, but first of all we'll draw it out and see what it is we expect to see. So what we expect to see, if that's sigma and that's j omega, we'll expect to see a pole whenever the denominator is 0, so that's when s minus j omega equals 0 and s plus j omega equals 0. So we'll expect to see a pole when s equals plus or minus j omega. So a pole at some point here and a point here. Now we also expect to see a 0 whenever the numerator is 0, that's when s equals 0. So we expect to see a 0 here. So let's go and have a wee look at this in MATLAB and see if this is what we get. Okay, let's see MATLAB. Okay, so what we have here is our sigma axis down here and our j omega axis along here, and as we see we've got everything runs along the sigma equals 0 axis, which is here. Okay, and we've got a 0 at the 0 point, so you can see that dip there. Okay, and that's the 0, and we've got a pole when j omega is -1 and a pole whenever j omega is 1. Okay, so that's exactly what we're expecting to see. So let's move on and we'll look at the sine function. So we know we can write sine out as sine omega t equals e to the j omega t minus e to the minus j omega t all upon 2j. So as in the previous example, we can replace our value 1 with 1 upon 2j. So the Laplace transform of sine omega t is just going to be 1 upon 2j upon s minus j omega minus 1 upon 2j s plus j omega. So the common denominator is going to be s minus j omega, s plus j omega. Okay, and the top line there, we're going to have our 1 upon 2j times our s plus j omega, that's j omega, minus 1 upon 2j, and it would be our s minus j omega all upon our s minus j omega, s plus j omega. Okay, so all we've done is just taken these two together, okay, and then we had to multiply by this one for this and this one here for the other one. Okay, so we're going to end up with the denominator is just going to be the same, so we're going to have our s squared plus our omega squared, but the numerator, we're just going to get our a half js minus half js, okay, that cancels, and the omega will be minus minus, which is plus j omega. So we'll have plus j omega, the j's cancel out, and it's a half plus a half of it, so you're just going to be left with your omega, where the real part of s is greater than 0. So that's the Laplace transform over sine omega t. Okay, so now we're going to look at that in MATLAB as well, but we'll do a little drawing of the complex surface and see what we expect to see. Okay, so what we're going to have is our sigma and our j omega, and it's going to be the same as for the cosine. So when the denominator is going to be give us our poles, so s minus j omega equals 0 and s plus j omega equals 0. So we're going to get our poles at s equals plus and minus j omega, so somewhere up here and there. Okay, now there's no zeros in this because there's no factor of s in the numerator. Okay, so that's what we're expecting to see. So let's have a wee look at that in MATLAB. So this is our sine, so that's our sine omega t there, and you can see sigma equals 0, so it all lies in the sigma equals 0 axis, and we don't have any 0 here, we only have two poles, a pole at minus 1j and plus 1j. Okay, so that's exactly what we were expecting to see. So let's go back and we'll just do another couple here. Okay, so we could look at the Laplace transform of our e to the sigma 1 t times cos omega t. Okay, now we could quickly write that, and we could say that is, well, the Laplace transform of cos omega t is this s upon s squared plus omega squared, but now we're no longer looking at the value of s, okay, because we're multiplying by e to the minus sigma t, so it's going to be s minus sigma. So what we're going to end up with is our s minus sigma 1 upon s minus sigma 1 all squared plus our omega squared. Okay, and that's for the real part of s greater than equal to 0. Okay, so that's another Laplace transform there, and again we can look at that in MATLAB and we can see first of all what we expect to see. Well, if that's our sigma and j omega, we're expecting to see the same as the cos omega t, so we're expecting to see two poles and a 0, but the difference now is that it's been shifted in the sigma axis to the value sigma 1. So let's say sigma 1 is negative, so let's say sigma 1 is somewhere here. And what we're going to do is we're going to get the 0 shifted to that point and the two poles shifted as well. Okay, so that's what we're expecting to see. So let's go and have a wee look at it in MATLAB. Let's see if I can bring it up in MATLAB here. Okay, so this is our cos value. Okay, so that there is our surface there we're going to look at. Okay, so what you see here is our function cos omega t e to the sigma 1t. Okay, and you notice that it's similar to before, but the only difference is that the whole function has been shifted in the sigma axis back to, in fact the one we've chosen is it's been shifted forward to a value of 1. Okay, right, so and you can see the 0 there, so they've all been shifted in the sigma axis, okay, by a value of sigma 1. Now we can do the same again with the cosine value. Okay, so we can look at, sorry, the sine value, so we can look at the Laplace transform over e to the sigma 1t over, sorry, sine of omega t, and that's going to equal just our, and we could just rewrite that there as our omega upon s minus sigma squared plus omega squared. And what we expect to see is a similar thing again to the sine omega t surface. The only difference is that it's going to be shifted to a new value of sigma. Okay, so that's our value of sigma 1 there, and we'll have our two poles. Okay, so that's what we're expecting to see whenever we do this Laplace transform. So that's for real part of s greater than 0. Okay, so that's our Laplace transform there. So let's go in and we'll have a wee look at that in MATLAB. Okay, so write that out a wee bit neater, that's just a bit silly. We'll put that in. So that's going to be our sine function, sine omega t. Okay, so in MATLAB, let's go have a wee look at that. So MATLAB and our Laplace transform sinusoids. So this is going to be our, this one here, yeah. Okay, so again, what we've done is we've taken the sine omega t multiplied by e to the sigma t, and it's shifted it in the sigma axis back to by a value of 1. Okay, so there you can see it. Okay, so that's all there is to this video, and next video I'll move on to another property. Okay, thank you, goodbye.